So now that you have a kind of idea of how this lab is going to play out, we need to talk about a couple of different things. One is this equation that gives you the electrostatic force between two particles. Okay? Now, what you just saw in the lab, you would have like a source, like that one that you put in the middle, and then you would have like the test probe or the test charge that you would put somewhere out here. Okay? So this is this value of K, same thing, 9.0 times 10 to the 9 newtons meters squared over coulomb squared. So in this situation, like you have like a 1 nanocoulomb charge. Oh, okay, cool. That's going to be 1 nanocoulomb. Are you going to leave that in nanocoulomb?
No.
No. Okay?
No.
Nano 10 to the negative 9. I just go, oh, that's 1 times 10 to the negative 9. Okay? And then whatever that source probe, whatever that is out there that you're testing, okay, that might be 1, 2, whatever that is, and then you're going to divide by r squared. So this is giving the value of the force. Now, this force, because you're multiplying two charges together, both could be positive, both could be negative, you could have positive and negative. So this force, as shown by the electric field hockey simulation, could be attractive or it could be repulsive depending upon the charging. Okay? Gravity, you don't have to worry about that scenario. Gravity is just always, hey, this is what it is. It's always an attractive force. You don't have to worry about that. Now, if you look on, let me see. So, now, I'm going to change this up a little bit. What's on your equation sheet is you have this over Q. Okay? So, what this is giving you is the electric field, okay? And then you're going to have some unit of charge. So typically how this is used, everybody writes this as FEC, okay? They basically just solve for the force. Now, here's what's going to be important in terms of this. If you look at the units, that force has to be in units of what? Newtons. Q is going to be the charge, which is going to be in coulombs. So the value in terms of the units of your electric field, that's newtons per coulomb. Okay? Nice. So if you solve this for force, you have newtons per coulomb times coulombs. The coulombs cancel out. You get unit of newtons. Now, the question being, is that if you have a situation like this where you have the source and then you have that test charge, the question being is that what Q do you use? Either what you use what's creating the field as the source or you use the test charge. You always use what's creating the field. So that Q is always what's at the source of that field. It is not what you're using to try and figure out what the field is doing. It's kind of like this. If you look at little g equals big G m over r squared, if you're trying to find the gravitational acceleration of an object, you use, like, for example, the mass of the Earth or the 1 kilogram mass that you're dropping, or mass of the Earth. That's what's creating the gravitational field.
Yeah.
So this is a similar type idea. You use what's creating the electric field, not what's in the electric field. So that always has to be the source. Now, the other way that you can do this, and if you look at here, you've got a different version of this directly underneath it. So what's on your equation sheet, you have 1 over 4 pi epsilon naught so
Wait, Barry, is the 4 pi, since it's like a sphere kind of looking thing?
no, it just is from, it comes from Maxwell's equations for.
Oh, that's right.
Don't worry about it.
Okay.
This is the technical version of it. This is how James Clerk Maxwell derived the equations. We just use K. So there's two ways that you can calculate the electric field. Okay? One is, there's two ways you can do this. One is you can use the force over charge, okay? Or you can use KQ over R squared. Now, if you look at the units, what are the units for K?
Meter squared over Coulomb squared.
Over Coulomb squared.
Okay, then you've got Q, which is going to be in
Coulomb squared.
Coulomb,
Oh, my bad.
Coulomb.
Yeah, my bad.
divided by
Squared.
squared.
Oh, you see what you get there?
Oh, the meter squared cancels out.
Meters.
One of the coulombs cancels
Newton
out.
coulomb.
You get newtons per,
Coulomb.
which is the exact same thing.
No way.
Wow.
Olivia,
What is that next to the 1/4
Epsilon.
that's just Q over R squared.
pi? Okay.
So all
Yeah,
you're
that's
doing
really
is
bad.
that constant K
What shack?
just takes the place of 1/4 pi epsilon.
What shack?
Okay? They list it as 1/4 pi epsilon naught, but nobody actually uses that. Everybody just uses 9 times 10 to the 9. Okay? So
I'm gonna get
it's there, but no one uses it.
You won't. I trust.
Now, next one down. So down here a little bit, you've got E equals delta V over R. So there's a third way that you can do with electric fields. What?
Both Q's, the Q's of the source.
Yes. It's always the source. It's always the source. Now, this is delta V over R. So with this one, typically, I don't know why they use R. Typically, that's a distance. It's delta V over distance. Okay. So here's how this plays out. This is going to be your voltage. Now, we just said what's one way to express voltage? Joules per coulomb. Okay? So I've got joules per coulomb divided by meters, right?
Indeed.
Now, what's another way to express joules?
Energy.
Force times distance.
Times height.
Newton
Meters.
meters.
Newton meters.
What do you mean talking height, bro? Why do you keep talking about height? Wait.
Hey, Gavin, probably just give up.
Wait.
It's okay. It's okay, Gavin. Me too.
D equals the square knot.
Hey, Nathan, you got a 0 on the left?
D equals 5'5".
But that's
So
not
let's
the
go.
same.
Let's not be mean.
But here's the cool thing.
D equals 165 centimeters. So
Here's the cool thing.
okay.
If you look at this in terms of voltage over radius, joules are Newton meters per coulomb. So if I take Newton meters per coulomb and then divide that by meters, the meters cancel out, you get
Newton per coulomb.
newtons per coulomb, which is the same thing as
FQ.
same thing.
That's actually really
Okay.
cool. That's too much.
So here's the point. Typically how this plays out, typically on this is how this is listed on your equation sheet, is that it's delta V over R. Typically it's a distance, not a radius, because it's the point between two charges. But if you solve this for delta V, you get voltage equals ed, okay? That's the more common way that this is used. Oh, voltage equals ed, okay?
Ed.
Just like technically you have E equals F over Q, but usually it's just
Fact.
Usually it's just fact. Okay?
Can we say
Now-
Ved in fact?
Huh? You have
Ed.
fed, you have V equals ed, and then you have fact. Now, there's one other equation that you need, and this will make sense later on. And your equation sheet lists this really weird, because your equation sheet technically does this 1/4 pi epsilon naught, because they're hardcore nerds. And then it has the sum of Q1 over R1, okay? So here's the other way that you can do voltage. So if you have more than one charge, voltage can equal, instead of the 1 over 4 pi epsilon naught, which nobody uses, this is just K, and then you can write this as Q1 over R1 plus Q2 over R2 plus, however far you want to go. Now, because the voltage can be the sums, okay, this is a big picture. Because the voltage can be a sum of charges over distance, if you go back to here, and let me get rid of all of this stuff, okay? Let me put a negative charge over here. So this is why if I have a positive and a negative, and I move that thing in between, that voltage effectively goes to
Zero.
Come on. I had it. Basically 0 in the middle. So when you have a positive and a negative, you can have a voltage defined as 0 in between, because it's the sum of the charge over the radius. Well, you're adding a positive charge and a negative charge, and as long as those are the same, where it's going to add up to equal to 0 is right in the middle. Now, however, if I have two positive charges, guess what?
-0.
It cannot equal to 0. Why?
Because they're additive.
Because
it's
they're
two
adding two
additions.
positive charges together. Okay?
So then 2 negatives has to be less than 0.
Yeah, so two negative values, you can't have 0 voltage either. Now, an interesting thing happens. Let me go back to here. And this is going to be one of the main parts that you need to get out of this lab. So if I have a positive and a negative, I can have in the middle effectively a voltage of 0 because I'm using the sums, right? But, if I put this field sensor in between them, notice that this is volts per meter, okay? Right?
Oh, yeah.
Volts per meter. So that's joules per coulomb, right? Okay? Over meters. So notice with this one, no matter where I move this, I can't make that go to 0. But I can have voltage go to 0. So here's two disparate ideas. If I have a positive and a negative, I can't make this electric field sensor go to 0. Because if I put a positive test charge in the middle, it's going to get pushed by that positive and pulled by the negative. So if I have a positive and a negative, I cannot have an electric field that's 0. But I can have a voltage that's 0. Okay? So if I have a positive and negative, the electric field can't equal to 0, but my voltage can. Okay? But if I have two positive charges, my voltage in the middle can't go to 0 because I'm adding two positive values together. But could my electric field go to 0 in between?
Yeah.
Effectively 0. Why?
Because it's like we're both pushing the same.
They're both pushing the same amount. So you have, if you have a positive and a positive, or two negatives, the voltage cannot be 0 in between. But the electric field can. But if you have a positive and a negative, the voltage can go to 0, but the electric field can't. Right? That's the big idea. So, in terms of this lab, here's what you've got. So, what you need to try and get through today, and if you do this right, you won't have any problems at all, is get through part 1. Okay? So it's going to involve some dimensional analysis. It's going to involve some equation work. You're going to have to draw a simple graph. I'm going to give you a half sheet of paper to draw a graph on. So you've got some different equations that you need to use, and I try and lay those equations out. But pay attention to where I want these charges placed. Okay? That's going to be vital that you place these charges where I tell you to in terms of that distance. So we're going to finish this up tomorrow. Just get through part one. Once you get through part one, you're good. I'm done.
You know what mountains are?